Hello, welcome to the conference Selected Areas in Cryptography 2021. This video presents the paper ZKAttest, Ring and Group Signatures for Existing ECDSA Keys. This paper is authored by Armando Faz and Watson Ladd from Cloudflare and Deepak Maran from Cornell Tech. My name is Armando, and together with Watson, we're going to present this work. This is the outline of our presentation. We first start with the motivation of this project and present the problem that we want to solve. We present our solution that we call ZKAttest. We describe its internal and its application on ring and group signatures. We also show some implementation aspect. We finalize with the conclusion of this work. The increasing use of public key cryptography enforces the use of secure mechanisms to store key securely. It is not common to find hardware devices with private keys embedded, and these devices only provide limited access to users, for example, restricting only the operation that can be done with the key, for example, only signing with ECDSA. Another disadvantage is that this key may not be used in ring and group signature schemes, because these schemes usually assume access to the private key. Some examples of these situations are hardware tokens, smart card, HSMs, and hardware authenticators. So let's see more closely this latter case. In some authentication systems, service requires the user some proof of possession of a hardware authenticator. The user uses his device and performs a physical action or gesture, for example, touching on the screen or pressing a button. With this action, the authenticator sends an attestation, which usually is a digital signature using the private key that is embedded. And also, it sends a public key for verification of this previous signature, together with a chain of certificates that links to the device manufacturer. Thus, the service can verify that the signature validates and the certificate chain corresponds to the trusted manufacturer. However, there are some privacy issues when presenting an attestation. For example, the attestation can contain some information that can be used to vulnerate the privacy of users. For example, a certificate chain contains information about the manufacturer or the model of the device. So, in order to protect the uniquely identifying devices, sometimes public keys are shared between a batch of devices, but still the service can learn the public key. So, our potential solution to this is to prove in zero knowledge that the attestation is actually valid. In this setting, we evaluate the existing options in the literature, for example, using generic proof system. However, they become difficult to use and are in general slow. Also, existing ring signatures require access to private keys, which is one of the main barriers to meet our goal. It is unlikely that attestation method change, as they require to modify hardware. So, for this reason, we present a concrete solution to this problem. Our proposed solution is called ZKAttest, which is a Sigma protocol that proves in zero knowledge that an ECDSA signature is valid using a committed public key. Our system does not require generic proof system and also supports a standard signature algorithm such as ECDSA. Additionally, no changes are needed to hardware devices. That makes our protocol compatible with existing hardware authenticators. Our protocol allows to instantiate ring and group signatures and allows some other applications. We present a proof of concept implementation targeting a browser environment. Okay, let's see more details about the protocol. First, let's recall a bit about the ECDSA signature scheme. ECDSA works on an elliptic curve with generator G of order n. The key generation produces a pair of keys where the private key D is chosen at random, and the public key Q is equal to D times G. To sign a message M, we first compute T, which is a value derived from the hash of a message. We then perform a scalar multiplication k times g, where k is a random scalar. This will produce a point big R, where the x-coordinate is denoted as little r. After that, S is computed using the following equation. And finally, the signature of the message is the pair little r s. For verification, we need to check that this equation holds using the public key Q. So in order to prove validity of a ECDSA signature, we realize that the current verification equation must be reshaped in order to be more friendly with zero-knowledge proofs. And we arrive to this second equation. Basically, we isolate Q, the public key, in the right-hand side of the equation. So we can commit the public key and verify that the equation holds. The first thing to note is that we don't reveal the S value of the signature, so it remains private. Also, note that the point R doesn't depend at all on the public key. So this allows to do to compute two proofs. First, the prover can transmit R and a commitment to C to demonstrate the correctness of the commitment of C times R. In order to do this, it uses a proof of scalar multiplication. The second thing to prove is using a committed public key Q that can be used in a proof of point addition to check that the verification equation actually holds. Now, I'm handing over to Watson, who will continue with the presentation.
Good morning. My colleague has introduced ZKAttest and has discussed some of the properties of the scheme and its motivation. I will be discussing the internals of the proof techniques and some of the applications. We start by recalling standard techniques to prove that committed values are sums and products of other committed values for Peterson commitments. This is the work of Karkamesh and Stadler and consists of proving linear relations amongst discrete logarithms. For multiplication, auxiliary commitments are required. We can combine these techniques to prove that that x and y coordinates of a point are the sum of other x and are the result of an elliptic curve point addition with other committed x and y coordinates. This is fairly straightforward and is discussed in detail in our paper. Scalar multiplication, however, is more complicated. While we could translate a circuit for scalar multiplication into a set of discrete logarithm proofs, such proofs would be extremely complicated for the prover to prove and take up lots of space, as well as be expensive for the verifier to verify due to the size of the circuit. We therefore apply a different technique. Before we get into the details of the technique, we'd like to recall that there are two different groups we're going to be talking about. One group is the group of points on a standard curve, like P256. The other group is the group of points on a curve with a particular order, the field size of the P256 curve, the size of the base field. This curve we call a Tom curve due to the close association to the NIST curves, which were created by Jerry Salinas. We generated these curves through the complex multiplication method as described by Brocker in his doctoral dissertation. This generation took a few minutes on the laptop I'm now speaking on. With that in mind, we'll discuss the scalar multiplication proof. Both parties share a commitment to lambda over the NIST curve, as well as coordinates of lambda times g, where g is one of the generators we use in generating the Peterson commitment to lambda. The prover picks a random value alpha and commits to alpha in the NIST curve, as well as the coordinates of alpha g and alpha minus lambda g. And verifier sends 0 or 1. If the prover gets 0, the prover opens commitments to everything but the coordinates of alpha minus lambda g. This demonstrates that the prover could not have cheated by committing to other values. If the prover receives 1, then the verifier opens the coordinates of alpha minus lambda g, proves that alpha minus lambda g plus alpha g equals lambda g, and verifies that the commitment to lambda agrees with the commitment to alpha. This proof is largely taken from existing work, and we cite this in the paper. However, we've had to modify it to ensure correctness by including the check that the commitment to lambda agrees with the commitment to alpha. We iterate this proof this proof has a soundness of 1/3. And that's because in the one case, the proof of correctness to addition requires 2 possible transcripts to extract a secret, and therefore we iterate this many times in order to get an acceptable level of security. We now discuss, now that we understand how to get a proof that a ECDSA signature verifies under a committed key, let's discuss some of the ways we can use this. One of the first applications, and the one that's really the motivating application, is ring signatures. We have a list of public keys, the ring, and the signer knows the secret key for one of the keys. The signer takes that key, commits to it, signs the message M that they want to sign, and then creates a proof that they have an ECDSA signature under this key. Then they combine this with a Gross-Colwies proof to show that their key is indeed in the ring. Intuitively, it's clear that this works. And indeed, in the paper, we formally prove unforgeability via a proof that can be summarized as extract the ECDSA signature. And then we also show that our ring signature achieves anonymity against full key exposure. This proof can be aptly summarized as fake everything the adversary sees, using the fact that these zero-knowledge proofs have honest verifier zero knowledge / in the raw model, there's a forger. While very brief, we do go into some more detail in the paper about how to prove these things, although it is fairly intuitive that a scheme like this could work. There are some other applications. So instead of applying a Groth-Colwies proof of membership, why not a Bayer-Groth proof of non-membership? And this can be used in applications where you wish to show that a key is not on a block list. This has sort of the complement of what we already have, and there's certain applications where it's quite useful. For instance, if you wanted to deal with revocation. With accumulators, we can get a group signature. However, many accumulators, like RSA accumulators, have the property that anyone can verify that a key is in the accumulator, and therefore we don't have the same anonymity properties. This does, however, produce a group signature scheme, which may be of some interest. Indeed, we earlier implemented a group signature version of our scheme before deciding to use a Groth-Colwies proof. We can also apply this problem to one of cryptocurrency storage. Many existing hardware security modules only support ECDSA. By using a proof to spend instead of revealing the signature, we get an anonymity preserving cryptocurrency that can work with existing hardware security modules. This is superficially similar, as I understand it, to the approaches that Zcash has taken in their later iterations of their design, although I'm not by any means an expert on how exactly our scheme differs. We also have a proof of concept implementation. Because of the application we were trying to make possible, this is aimed at the browser and is written in TypeScript. We use 2 optimizations that are quite common and are necessary to get performance speed up, namely batch verification of linear relations. Rather than verify a whole number of individual equations, often with 2 or 3 or 4 terms, we take a random linear combination and verify that this random linear combination is 0. We also use simultaneous inversion, aka Montgomery's trick. The code is available on GitHub at the link below, and we welcome comments and improvements. In conclusion, we've demonstrated a proof of knowledge of an ECDSA signature, allowing for support of existing keys in hardware authenticators for ring signatures and other applications. We've also shown that complex multiplication is useful to make elliptic curves for zero-knowledge proofs. And with that, I'd like to end my presentation and thank you all for attending SAC 2021.